Hello, hi everyone. Welcome to another episode of Stark at Home. My usual first question for those who attended: can you hear me? So, if you can please type in the chat. Can you see? You're supposed to see four guys. If you can type, if you see us and hear us, sort of a collective mic check. Just waiting to see on the chat that we can be seen and heard. Okay, thanks, Supremax and everyone else. Okay, thanks. Terrific. So I'm Eli. Very happy to be joined here with three of the co-authors of a paper that will be the focus of this episode. So we have here Leo Goldberg from Starkware, co-creator of Cairo and lead engineering for StarkNet. We have Professor Jeremy Avigad from Carnegie Mellon University. We have Dr. Yoav Seginel, and they are three of the five co-authors of the white paper that will be the focus of this talk. So I will just speak very briefly and say two things. First of all, if you have questions, please use the Ask a Question button to put it there rather than the chat. And ever so often, we'll go there and answer the question. So please use it liberally for all your questions. And now a little bit about just the topic. So we are using Stark proofs running over some framework that has a virtual machine called Cairo that Leo and co-authors developed. And it's very important to us. So by now there's more than $1 billion locked in value and settled ongoing through programs that are written and argued over the logic that is Cairo. So it's really, really important to know that there's no bug there. The analog of the Pentium bug, from the 90s, that everything's okay. And it's a very complicated system, even for humans to sort of understand. So what the authors of this white paper did and are continuing to do is to rely on machines to help the mathematicians, these co-authors and their collaborators, know for sure that everything is sound and working. And this reliance on computers to help you prove theorems is a very recent, it's a very old trend, but recently it's been successfully used in more and more stuff. So that's the exciting introduction to this episode. And with this, I will hand it over to Professor Jeremy Avigad and take it from here.
Yeah. So thank you, Eli. So as Eli said, the project we're going to tell you about is a formal verification of a piece of the Cairo toolchain. And so what I'm going to do now is try to give you some background on formal verification and formal mathematics more generally. There's a long history of designing symbolic languages to represent knowledge and represent rules of reasoning, but it really became a proper mathematical subject in the 19th century, with the work of Boole and De Morgan and Peirce and Schroeder and so on. And towards the end of the 19th century and the early 20th century, people developed formal axiomatic foundations for mathematics. In the late 19th century, there was Frege with his Grundgesetze, and then Zermelo and Russell and Whitehead in the early 20th century. And the idea is these axiomatic systems give you precise symbolic descriptions of mathematics. So you have precise descriptions of mathematical language and rules for forming well-formed statements. You have axioms, so these are the starting statements for mathematical reasoning. And then there are very precise rules that you follow to derive new statements. And very quickly, the discovery was that these formal systems really are adequate to represent mathematical reasoning. So these conventional methods of mathematical proof can be formalized in these systems, at least in principle. And what's happened over the last few decades that's really interesting is that phrase in principle has turned to in practice. So the idea is we can now use computational proof assistants, interactive proof assistants, to construct formal axiomatic proofs of mathematical theorems. And the first systems for doing this, they appeared fairly early, in the late 1960s and early 1970s. Um, uh, but so the idea is that you sit with the computer and you work interactively, and what you're trying to do is convey to the computer a mathematical proof, enough information to construct a formal proof in kind of a stylized programming language, a proof language that looks a lot like a programming language. So I'll give you an example of that in just a minute. Um, but so that's the idea. So you work with the computer to construct a formal proof. And in most systems, when you're done, when the computer signs off and says, yes, the proof is correct, somewhere in the memory of the computer, there's actually a data structure that represents your formal proof. And so this is an object that you can export, that somebody else can check with an independent checker, right? You really have a formal proof of correctness of your mathematical claim. And so these days, there are a lot of systems out there in use, systems like HAL4 and Cook and Isabelle, HAL Lite, ACL2, PBS, MetaMath, and so on. So there are a number of systems out there. The system that we used is called Lean. It's one of the newer ones. And so that's the platform we'll be highlighting in this presentation. But that's the basic technology. So let me pause and ask. So what I'd like to do is in a moment, I'll share my screen and try to give you a little bit of a flavor of how formal verification looks. But before I do that, are there any questions, or is there anything I can try to clarify or explain? Okay, so I think we're good. So Ellie, maybe if you can sort of keep an eye if a question pops up, let me know.
Yeah, I did. There are two questions that are not relevant. One is about translating the episode, and another is this thing that if we have time at the end, it's tangential. So yes, but please use the ask a question button for questions.
Okay, good. All right, so let me try sharing my screen. Let's see, hold on a second. Share, sorry. Okay, and let me put that to the side. So if all goes well, you should be looking at a browser page and the words Lean Community there. So maybe somebody speak up and let me know if that's not the case. But what I want to show you now is just some home pages for the Lean Mathematical Library. And it's easy to find this. If you go to your browser and if you just type Lean Community, it should come right up. But here, you can find out more about Lean in the libraries, and there's documentation, and you can meet people involved in the community, and you can find out that there is a social media chat group on Zulip that you're welcome to drop in and say hi to people. But what I want to show you is that you can actually sort of access the library from here. If you go to API documentation, you see on the left side there's MathLib. This is the mathematical library. And so, for example, if you decide that you're interested in number theory, you can go look at the number theory files and theories that are there. And so, for example, you might find this primes congruent to 1 interesting. So there's a lovely theorem that goes back to Fermat that an odd prime can be written as the sum of 2 squares if and only if it's congruent to 1 modulo 4. Oh, wait, let's see, that's not the one. This is the one I want, sum of 2 squares. Sorry, that's the theorem I had in mind. So the theorem is that an odd prime can be written as a sum of 2 squares if and only if it's congruent to 1 modulo 4. And here is a formal statement of the theorem. So it's a theorem net dot prime dot square adds square. But if P is prime and is congruent to 1 mod 4, then there exist A and B such that A squared plus B squared is equal to P. Right? So this is a statement of the theorem.
Jeremy, can you enlarge a little bit the fonts on your screen?
Yeah. How's that? Is that better?
Or even bigger? Much better.
Good. Okay. And you can click on the source. The library is all in a repository, and so you can actually find it, find the formal proof online and browse the library there. But I want to also point out that so, for example, if you click on the definition of prime, you can find the definition of prime. So there, P is prime if and only if P is greater than or equal to 2. And for every natural number M, if M divides P, it's equal to 1 or equal to P. Okay. And then even further on, if you see the natural numbers here, you can actually jump to the foundational declaration of the natural numbers. So this is one of the few axiomatic bases in the system. So it allows you to declare inductively defined types. So this roughly says that the natural numbers are axiomatically, they're defined inductively by a zero and a successor. Okay, so this declaration tells you that you've got a zero, there's a successor, which is a function that takes you from a number to the next one. And you get a principle of induction and a principle of recursion. Okay, so yes, that was the first thing I wanted to show you. So you can really find the library online and browse and see what's there. And so the other thing I want to show you is just give you a little flavor of how it looks to kind of work in such a system. So here, this is lean running. So as I type, lean is kind of checking and giving error messages and so on. But this is so the well-known theorem or fact that was given to Gauss as a school child, or Gauss discovered as a school child. So this is the theorem that if you add up the numbers from 0 to n, the sum is equal to n times n plus 1 divided by 2. Okay, so here, if you hover over range, the tooltip will tell you that by definition in the library, range n is the set of natural numbers less than n. So range n plus 1 is the set of numbers from 0 to n. And this says, this is the summation symbol. So this says if you sum up all those numbers, what you get is n times n plus 1 over 2. And so when you declare this, your intention of proving it, lean then expects you to give a proof. And here, that's what these lines do. They're instructions that tell lean how to construct a proof. So symmetry, if you look, just kind of turn the equation around. But then we apply a theorem that says to prove A divided by B is equal to C, it's sufficient to show that B times C is equal to A. So that was that one. And there's a side condition. You need to know that you're not dividing by 0. So, you have to show that 0 is less than 2. But fortunately, Lean's automation can prove that. So then we have to show that n times n plus 1 is equal to twice the sum. And this is something that, you would do by induction, right? So we give Lean the command induction n. We say do that by induction. And then Lean shows us that there are two cases, right? There's a base case. There's the 0 case. That's the case nat 0. And there's the successor case, right? So in the base case, it's kind of a trivial case that 0 is equal to 0. And so Lean knows that 0 times anything is equal to 0 and so on. So the automation in Lean is good enough to do that. So that gets done. And then, in the successor step, so this n.suck is just another notation for n plus 1. But then it's just a calculation involving the inductive hypothesis, and that's what's going on here. So you do a calculation. RW stands for rewrite. So you apply some equations and rewrite. And then you just get a little bit of algebra, and then there's automation in Lean called ring, which solves that. And when you finish the proof, you get this kind of very happy celebratory emojis, goal accomplished, and then you're all happy and you go out and celebrate. But the point is, when you're done, you've proved a theorem, right? So it's stored in Lean. If you ask, Lean about this proof, it says, yes, I know this theorem. You've proved it. It's the theorem that for every n, the sum, is equal to. Let's see. I wonder why it's. So yeah, the sum is equal to n times n plus 1 over 2. And in fact, you can ask Lean to print out the proof that you just constructed. And because we use automation, I mean, it's this kind of big, horrible, ugly expression, that goes on and on. So this is not, I mean, you want to read the source. You don't want to read kind of the internal representation. But the point is that it's there, right? So when you prove something formally and all the rules are there and it's stored in the system, and that's what's been checked by the computer. So let me stop sharing now. So let's see. So where did we go? Okay, so yeah. So before I pass the microphone over to Lior, let me just say a few more words. So this gives you a picture of what it means to verify mathematics.
Yeah, Jeremy, there was one question that is relevant. I'll read it out. Is
Please.
Lean formally proved? Guilam is asking.
Yeah. So it's a very good question. So a question that often comes up is you're using Lean to check the correctness of mathematical proofs. And so how do you know that Lean is doing the right thing? Why do you trust Lean? And the short answer is that Lean is built on an axiomatic foundation called dependent type theory, which is well studied and people understand. Its correctness has been proved relative to set theory or other axiomatic foundations, so we understand it pretty well from a theoretical standpoint. And then the system is implemented, the part that actually checks proofs is implemented very carefully to check the rules. Now, it turns out that one further thing that one can do is then try to model the Lean program itself and then prove its correctness relative to that specification. So that would be sort of an extra level of verification. And that has not been done with Lean. That has been done for other systems. But the short story is that roughly the checker part of Lean has been written very carefully. And not only that, people have written other checkers. So there are independent checkers also checking the correctness. But you're right. So your trust in the proof really comes down to your trust that the checker is doing the right thing.
I'll just answer some other question that appeared even before. Will it be included subtitles or transcript? So not here because Crowdcast doesn't support it, but everything will be uploaded to our YouTube channel, and we'll try to add subtitles there. Sorry, please continue.
Yep. Okay. Okay, so now I've told you what it means to verify a mathematical theorem, but we've also told you that this is a project in software verification. So then the question is, what is it to verify software? And the short answer is that, well, verifying software is just proving a theorem. So the idea is if you want to verify the correctness of a piece of hardware or software, what you have to do is write a mathematical model of your system, write a specification of what it's supposed to do, and then you're just proving a theorem that your artifact, your piece of hardware or software, meets its specification. And so again, this is a practice that has been around for a few decades now, and it's gaining currency in industry. So, for example, Amazon and Facebook and Apple and Microsoft have people doing verification along these lines. And in fact, for every one of me, sort of interested in using theorem provers to prove mathematics, there are a lot more people using it to verify hardware and software. But the connection is that verifying hardware and software really is just proving theorems. They're just theorems of a particular computational nature. And so to tell you more about that, I think this would be a good time for me to pass the microphone over to Lior, and he can tell you about Cairo and the Cairo project and what in particular we were trying to verify with this project.
Okay, you can hear me, right?
Yep.
Okay. So what we did in this paper is we are using Lean to prove some things that I'll explain in a minute about Cairo. Cairo is a programming language which we built. The idea of this programming language is that it allows one party to prove to another party that a certain computation was executed correctly. For example, you can do it without revealing all the information. The other party, or let's say it in another way. One option to prove that a certain computation was executed correctly is to ask the other party to execute the computation itself. But this is not very efficient, and it turns out that there are better ways to do it. So Cairo is a programming language that allows you to do it. It's built on top of the Stark proof system, which also gives you the same ability to prove that a certain computation was executed. And the difference between the Cairo as a proof system and Stark is that Stark expects the computation to be described as a list of polynomial equations, and writing and this is over a finite field, and describing a computation as a list of polynomial equations is a very difficult task. Cairo, on the other hand, is a programming language, and writing code is much easier than writing equations. For example, with code you can do branches and for loops and so on, which you can't do when your only tool is equations. So Cairo, the goal in Cairo was to help with this gap. Now, let's talk about Starks and errors. Errors is the input for the Stark prover. It sends. So R is algebraic intermediate representation. Basically, an R is a table, two-dimensional table of field elements on which you can write your equations, your polynomial equations. And Cairo, basically, what we did is we used these polynomial equations to describe a processor, a CPU, which knows how to run the instruction set that was created for Cairo. And this is how it works. So you write code in Cairo, and this code is executed on this imaginary CPU, which is simulated by equations. The equations enforce that the CPU does what it should. And for this, we had to write polynomial constraints that describe what the CPU, how the CPU should behave. And this is the place that we are going to use Lean to prove. So once we have this list of equations that describe the CPU, we need to know that we did a good job in writing these equations. So basically, there are two sides: the completeness and the soundness. So completeness means that if you have a program and you run it and you get the values for the field elements, they should satisfy the list of the equations. And soundness means that the other way is also true. So if the list of the equations is satisfied, then it means that it corresponds to a valid computation. Usually checking for checking completeness is easier. You can use the usual tool of unit tests and all the tools that you are used to from programming. Basically, you can test a lot of cases and make sure that in all of these cases, the values that you get to the table of field elements indeed satisfy the equations. Checking for soundness the other way is much more difficult. It means that for every assignment that satisfies the equations, there should be a corresponding valid computation trace. And how can you enumerate over all options of satisfying assignments? And by the way, the fields that we are working on are pretty large, so basically you can't even enumerate on one cell in a feasible time. So there are certain ways which we did before this paper in order to convince ourselves that we didn't forget any constraint, and the constraints are covering what we wanted to say. And these were more like unit tests that were, so we made the problem much smaller in certain ways in order to try to simulate the best we can about these constraints and whether or not they indeed cover what they should. But Lean provides you a much another option to do it is an audit, a human audit. So this can work, but people can miss stuff. So we we did what we could to make sure that the polynomials should be correct, but without tests, you can't be sure that you didn't miss anything. So what we did with Lane is actually to prove a theorem that says if the polynomial equations hold, then the computation that is described is valid. And this is something that actually is very powerful, much more powerful than both soundness test and human audits. I think this is what I wanted to say. So other questions? Let's see. The Cairo compiler is open sourced. So the question, will it be open sourced? So the answer is yes, it is open source, right? So it's source available. I'm not sure about the exact licensing, but the source is available. You can check it out in the repository. Are there any other questions? Okay, I guess not. So I think the next part, Yoav will demonstrate, will show the theorem. So we will show both parts, what implies what. So Yoav.
Thank you. So I would like to start by saying that the whole proof which we are now discussing is available on GitHub. I'll show you the repository so you can find. So here is the sorry, just one moment, please. Somehow, there it is. Yeah, I'll share it. So here it is. This is the repository. We can later share the link again. And everything I'm going to show you now is available in this repository. What I will show you is exactly what you will get if you download this repository following the instructions here and simply run Lean on it. So please try it at home. So now I will actually show you what's in there and how that actually proves the things that Leo talked about. Of course, no intention of getting into all the details, but just to give a feeling of what it means to construct such a proof and what parts this proof consists of. So again, I'll share my screen. There it is. Hopefully you can see my screen. So this is a theorem in Lean, and it is called final correctness. So you can imagine that this is the end of a rather long proof. And this basically here, I will go over that slowly and show you what the ingredients are which go into such a proof. One thing I will not talk about is the proof itself. So this is the statement of the theorem. We have here the theorem with all kinds of assumptions and the conclusions. And here, where the begin is, starts the proof. The proof perhaps looks inscrutable but short, but actually it's not that short because that proof, of course, makes use of other lemmas and so on, which are proven elsewhere. But as Jeremy showed you, if Lean tells us that it has checked this proof and it's okay, then if we are willing to accept that Lean is okay, and then you say, well, okay, let's forget about the proof. Let's look at what it tells us. I'm quite convinced that Lean has done its job correctly. let's show what it is exactly that we now know. So the statement of this proof actually has two large parts, one can say. So first of all, we have all kinds of inputs and all kinds of assumptions. And at the end, following this little arrow here, we have the conclusion. So if all these things hold, then we know that this holds. So what did we put into this? So basically, Leo talked about polynomials. He talked about a table with numbers, which which needs to satisfy the polynomials. But it also talked about a language and a virtual CPU that runs this language. So all these things somehow have to come into this one large theorem. So let's start. So here, for example, we have columns. This is the large table of numbers. We also have here, these are sets of polynomials, which we then apply to this table of numbers and say, well, these polynomials are satisfied. So these are the two ingredients on the side of the polynomials and the numbers that go into them. And these polynomials eventually go back to a very long list of things, lots of definitions, which you can then, if you ever read the Cairo white paper, you can compare them with this and see that it is really a one-to-one correspondence. Lots of things go into them, but they are basically all quite straightforward definitions, various structures. And then after all these definitions and definitions of all the columns, where which number sits where, and so on, at the end we have a list of polynomials. And these are the things we are going to, which are the input into our proof. And these are, by the way, generate automatically from the Cairo compiler. So we actually know that these really are the polynomials which are currently being used, because as you can see, they're quite many and quite complex. So one has to make sure that we are really encoding them correctly. So this is here. So we have the columns, and we have the claim about the fact that they satisfy that our columns satisfy the polynomials. Now, additional some probabilistic claims, which I will not go into, which basically say that cases which can go wrong are a very small set in a very large field. And then finally, we reach the conclusion. And the conclusion is this. It says that there is an execution sequence. So if all these assumptions, so the table of numbers, of columns of numbers, satisfy the constraints, then there is indeed an execution which starts where we think it starts, ends where we think it ends, and also is valid. In what sense is it valid? That every step is a next state of the previous state, which basically says this is a valid execution sequence. Now, this little thing, this next state, actually is where all our knowledge of what the Cairo CPU is encoded. Because to say that this state is a valid state, is a next state of the previous state, is to say, I understand how this machine works, and given that I know what I know, this will be indeed the next state of, or a possible next state, because things may be non-deterministic, possible next state of this execution. Another point which Leo didn't really go into this is that there's a very important notion of the memory on which this whole works. This memory holds both the Cairo program itself, data we provided, and also all the values which are used during the run of the program. And basically, it is one of the important points here is that it tells us that this execution will be a valid execution on this memory, which extends some piece of memory which is basically agreed in advance and somewhat encoded into the polynomials. So this piece of memory should, for example, hold the Cairo program we are talking about. And then when you combine these things together, you get to the conclusion that if your the columns satisfy the polynomials, and then there is an execution on some memory which agrees with the parts which are public and shared, for example, the program, and satisfies our definition of the Cairo CPU. Any questions until now?
So far there are no. I mean, there's one tangential question that we'll answer after we're done with the topics of this. I see. Actually,
Okay.
there is a question. Just 1 second. Yoni Levy is asking, what do you mean when you say possible next state, also known as next state, might be not deterministic?
Yeah. So this is into and the Cairo machine is that in itself is not deterministic, and it's and so in some cases even some things might be undefined, but that is not what is important. Is that there is some execution state which satisfies our definitions of the CPU. Later we will have to look at our programs and say, does this Cairo function actually produce the result that we expect it to produce? And if yes, then we have the conclusion that we have it. The states themselves are not that important. The question is it every sequence of states that we have? Does it satisfy does it give us the conclusion that we want from running this Cairo function? Like a normal program can check the clock of your computer, and then and that may enter the execution trace of that program. But still, you can say this function has. I know that it will do this or that.
Yes, the short answer is that the Cairo CPU is non-deterministic in some parts. It's up to the programmer to deal with it.
Perhaps, Leo, you can give an example as to why one would want it to be non-deterministic. Like, where could you use that?
So in general, non-determinism is a powerful tool for programmer. It's available in proof system in general because you have one party, the prover, that tries to prove something to the verifier, the second party, and the prover knows in advance what it wants to do. So, for example, if I want to prove that the square root of a certain number of x is y, the prover can compute the square root in any way it wants, not necessarily in Cairo, and then prove the other direction. It can prove that there exists, so it can prove that y squared is x. So in this case, this is a non-deterministic. If you read the program, it's a non-deterministic computation. You start with x, then you guess the value y and just check that y squared is x. If the verifier sees this program and knows that this program was executed, the verifier knows that y is the square root of x, and it doesn't care about the actual computation. So we moved from square rooting, which is not that easy algorithm to just one multiplication, which is rather easy. So this is one example where you can use non-determinism to write more efficient programs.
Mm-hmm. So you were speaking, or who's up next, or
Yeah, so I think I gave sort of a short overview of the proof. I think we can go into more details, but I'm not sure it's really necessary at this point.
Can you show the specs written in Lean of the?
Yes.
So I guess we won't dive into details, but it's nice to see how you translate the specs of Cairo as a programming language in Lean. This is basically taking the paper and the white paper of Cairo and writing the definitions in a very formal way.
Yes. So here, this is all in the file cpu.lean, and it really starts step by step by defining lots of structures. So the three registers which define the state, the program counter, and the other pointers, and here the structure of each Cairo instructions with the flags and the different offsets, and then a definition of the flags, and this is pretty much straightforward, defining step by step the whole language, and then here there are definitions which tell you, okay, if there are certain flags are set, what does that mean? And let's try the assert, for example. That's pretty nice. So here assert. So if there are certain flags, it tells you that two things, for example, agree, which is assert equal, and so the various flags of which define the different CPU operations are defined here, and here at the end we have this notion of a next step.
Yeah, so you can see, for example, something like a MOOCs, which chooses between a few options according to the flags of the instructions. These are all the FF things and TT.
Yeah, exactly.
I think there are questions. Ellie, do you want to
Yes, there's a question from Harish. How should we understand the fact that the claims are probabilistic? There is a 2 minus d, or there's a 2D, two-dimensional table of field elements that satisfy the constraint polynomial set. But the existence of that table is only very likely. Nothing can fall through that gap?
Yeah, okay, so this is a good question. So the answer is that by very likely, we mean that the probability that the claim will be false is around for something like 2 to the minus 200. So the way it works is as follows: the prover commits to a certain number of columns out of the two-dimensional table. Then the verifier chooses by random, picks 2 random values, for example, or 3 maybe, I don't remember, 3 random values, and sends the random values to the prover, which then have to complete the table by committing to the other columns. Now, if the prover is able to do it, the verifier takes it, the verifier accepts the proof, and there is a chance that the 3 random values picked by the verifier happen to be in what we called in the lean proof the bad sets, in which case the verifier will accept the proof even though the claim is false. So this is the opposite of soundness. But this is acceptable to us as the probability that the verifier will pick these bad values is very, very low, which means that the prover so the prover can cheat with probabilities 2 to the minus 200. This is much better than most of the protocols. There are places in the Stark protocol itself which have higher soundness error, so this is negligible.
I just want to add to that,
I mean,
the nature of interactive proofs, of which Starks are a special case, are that you get all of these savings in scale and succinct verification and zero knowledge. You don't get it for free. You pay something, and what you pay is that you need interaction, you need randomness, and there is always some probability of error. The nice thing is that the payments are sort of acceptable because, for instance, you can use relatively little randomness and little interaction and limit actually the probability of an error to something that is very, very, very small, like 2 to the minus 100, without that much work. And that's the beauty of the math behind it. But unfortunate as it may seem, and in contrast to the rigor of mathematical logic, so in contrast to what we see, to the validity and the certainty of, for instance, the lean proof or a standard mathematical proof, when it comes to proving systems in a system like Stark, but Snarks or any succinct ZK system has the same properties. You will have, you cannot avoid some probability of error. It's mathematically impossible to avoid that and still have things that are succinct and expressive.
Yeah. One last thing about this question. What we are proving in lean is that the probability of to choose these bad values is low. So this is the part, one part that we didn't dive into because it's complicated. And there are more questions.
Yeah, I can read them. Okay, so the question from Harish, meaning how does lean address it as it is a formal system? Okay, so I think you answered that.
I think so.
Okay, and then there's another question which I think we already addressed, but it would be good to go through it again. How do we make sure lean is correct itself? And how do we make that the program verify? Oh, and how do we know that the program that verified that lean is correct is correct? Let me add to that. How do we know that the machine, the chipset, this is a serious question, right? The chipset on which you're executing the run of lean, even if it is correct. So how do you know that this machine code, the sort of the NAND gates and the wires are correct? These are very good questions.
Yeah. So let me say that people who do formal verification are the most paranoid, least trusting people in the entire world. And so they're always very mindful of what you're trusting and where you're putting your trust. And then the game becomes you want to sort of minimize it. So as I said, the standard things that are done is that proofs are checked by a very small trusted kernel. The trusted kernel is duplicated. Sometimes the correctness of the trusted kernel is verified against some other semantics. So there are all kinds of things you can do. And then there are all kinds of questions. Well, you've written lean in a programming language. It's compiled. How do you trust the compiler? How do you trust, it's running on an x86. Why do you trust, the x86 instruction set? It's actually running on hardware. People have actually done back of the envelope calculations as to, what's the likelihood that a cosmic ray will come and hit your computer and flip a bit. So, there's never complete certainty. There've also been interesting, verification projects where people have tried to verify correctness, down to x86 instructions, and they've verified correctness of hardware. So the short answer is that there's never complete certainty, but you can get as close as you can. But the thing to keep in mind is that it's okay to be paranoid. I mean, it's fun to be paranoid. But if you've checked something with lean, unless you're barring kind of a malicious somebody who's hacked the system, or if you've checked something with lean, you have a much, much higher degree of certainty than just proving it by pen and paper. I mean, with the lean project, it was it formalized the white paper formalization, and the white paper was extremely carefully written. It was carefully checked, carefully thought through. But we human beings, we're always making mistakes. You're missing a base case. You're missing some corner condition. When you do it formally, you can't get away with anything. Every detail is checked. So yeah, there's always the possibility of some kind of implementation bug in the checker or cosmic ray or so on. But if you're really checking every detail, it's a much, much higher degree of confidence than you get otherwise. So there's never 100% certainty, but you really come pretty close.
I have to say another part which is more likely to be wrong is the definition of the theorem itself. So
yeah.
we are I think it's more likely that we made an error writing what we needed to prove and prove the wrong claim, than lean is making a mistake. So yeah.
That's another comment. So the theorem is only as good as the specification. So if what we've described isn't really the Cairo processor, then then our theorem is meaningful. So one thing that we were careful to do was when we verify the correctness with respect to the polynomials are taken, the output from the Cairo toolchain. And I gather in principle, anybody checking the Stark should be able to verify that those are the polynomials that were used independently. And as for the CPU specification, I mean, it's fairly short. It's about 100 lines. So, you can sort of read it and check it and convince yourself that it expresses the informal semantics. But let me mention that, this is also kind of a stepping stone. I mean, ultimately, we want to verify the correctness of Cairo programs, high-level Cairo programs. And so what you want to do is use the CPU specification as just kind of a stepping stone. So in other words, if you prove that a program meets a certain specification using the CPU semantics, then the correctness of the CPU semantics. So if you get a full end-to-end verification from the high-level specification to the polynomials, then the CPU specification just kind of drops out. Right? You've got a verification down to the polynomials, which is what you really, really care about.
So we have, I think, 3 more questions, and then one that is a bit tangential, and we'll answer it at the end. So if you have other questions, then please, now is the time. And we'll try to do it briefly because we're nearing the 1 hour mark. Okay. So the first question by Scott. Since this work is so specialized, how many people have reviewed the lean code that verifies that Cairo is correct? Is it 1 to 3, 5, 10, or 100? I'll give my attempt to answer, which is that, first of all, the nice thing is that each one attending here can sort of run it on their computer. And I mean, it's an automated proof. So that's...
You don't need to check the proof.
The important thing is that lean has checked it.
Yeah,
and
if you trust lean itself, and lean is unrelated to Cairo, so you don't need to check the proof at all. No one should.
Yeah.
Well, you could run it on your, you could run it on, you could download lean and run this particular proof on your machine, and but it would probably take a few seconds, I'm guessing.
Yeah.
But it's the end. It's about going over the definitions and making sure that they agree with what we intended, and the proof itself is really not the main problem here.
Okay, another question. How parameterizable is your lean proof? For example, say one day you decide to change the field size in the Stark proof system. Would the lean proof easily adapt to that? Same question for the other choices in the design of the Stark proof system. That's a beautiful question.
Yeah, so the only assumption is that, hold on a second. I'm sorry. So the only assumption, so for most of the formalization, we only assume that the field is a finite field. We don't even assume it need not be the integers modulo prime. I mean, it might be higher dimensional over the prime, over the prime field. So most of the formalization just depends on the fact that it's a finite field. And then when we reason about instructions, we have assumptions that it's big enough to contain the encoding of the instructions. But other than that, it's really independent of the size chosen.
Yeah, but if the design of Cairo changes, of course, we'll have to change. So a lean proof is basically like writing a proof in a mathematical paper, except that you do it in the lean programming language. So of course, if the specification changes, you will need to change your proof.
I would also like to add that one of the nice things about working with Lean is that if you make a change in some of your definitions or in one of your assumptions or so on, it very quickly shows you where things start to fail. So if somewhere in that whole construction there's a lemma where suddenly things don't work out right, it will tell you here you have a problem. This lemma doesn't work anymore. And very often you can it's enough to make a small fix to get that to work. So it's very much not only, it really shows you where the change is and what it implies.
Okay, next question. By the way, I want to throw in a question that I'll type in a minute. But so are all of the probabilistic errors on the side of verifier choice? How much room is there on the prover side to affect the error rate? Question by Brock.
So I'm not sure that I fully understand the question, so I'll try to answer what I understand. The soundness error comes from the probability that the verifier, when the verifier has to pick random values in the protocol, it will choose values that allows the prover to cheat. So in this sense, it's on the verifier side. The prover can't. Maybe the prover can lower the probability, maybe by generating an honest proof, for example. But we bound from above the probability that there will be a soundness error.
I can add to that that the general theory of proof systems is one in which there are two notions of error that you were asking about. There's something called the soundness error, which is more on the verifier side, and there's something known as the completeness error, which is more on the prover side, which is, what is the probability that a true statement in an honest prover will still get rejected. Now, in the proof system, in the Stark proof system that we're building, and in almost all proof systems used, let's say within blockchains, you build them with perfect completeness, which means that there's no probability of error on the prover side. It's only on the verifier side. So it's very pleasant. It means that if you're proving a correct statement and you're behaving honestly, you will generate a proof that will, with probability 1, will be accepted. I will mention that for a variety of theoretical reasons in other proof systems, often it's very useful to have non-perfect completeness. So one very famous example, there's a famous PCP theorem paper by Johan Hastad titled "Some Inapproximability Results," where some interactive like proof system is used to show very tight hardness of approximation results, and there it's very important that the prover have non-perfect completeness, so some probability of error for good reasons. Anyways, so now I have a question that I added. So it's a general question: how far are we from having all serious theorems proven by Lean and similar systems? How far are we from having all math papers verified this way?
Pretty far. The technology is just starting to gain currency in the mathematical community, but it's still pretty small. There's a very small number of core mathematicians, and the problem is that it's really a very high standard of correctness. It's really a lot of work. It's really sort of painstakingly, it's painstaking, and so. What we need to get there is better engineering. We need better libraries, better automation, better tools. I don't know if we'll ever get to full verification, but we can verify a lot more. I think in the short term, you want to pick your battles. You really want to verify the things that you're really uncertain about. And so with hardware and software verification, it's most important to go for safety critical systems, or systems where there's money riding on it and so on. You sort of decide what you care most about. and then you know go after the things where there's the most uncertainty. Similarly, in mathematics, there's a lot of mathematics out there. You know, in the short term, we need to sort of pick our battles well. But yeah,
That's comforting,
it's a long road.
That you know, in our hats as mathematicians, we still, you know, we're still not being replaced by machines.
Well, so what we've described is only checking the mathematics, right? We still need the mathematicians to produce the mathematics. So the idea is that
may also be replaced, right? I mean,
you're just saving, Ellie, you're just saving the referees' work here.
Right. So, okay. Right. No, but I'm saying just like cars are starting, I mean, you know, machines are starting to drive and they're already talking and playing chess better than us, and maybe they're going to soon replace us also when it comes to proving theorems.
Yeah, I don't worry about that. You know, it's the computer is a tool, and as the computer can do the things we do now, then we'll just find even, you know, we'll be able to think even bigger ideas and do even bigger and better things. So.
Spoken like a true tenured professor. Okay, there's another question. My understanding is that there is still debate about how random is random in programming. Does the randomness that I guess that your Lean and Cairo use satisfy all requirements?
Yeah, so I think it has to do, okay, so what I described previously is the interactive version of the Stark proof, where the verifier gets to pick random values, and then you can ask whether or not the randomness used by the verifier is actually uniform. But this is not exactly what we are doing. We are using the non-interactive version, which uses the Fiat-Shamir heuristic in order to replace the randomness by a hash function on the things sent by the prover. And for this we are using in our proofs we use the catch-up hash function, which is considered to be safe to the best of what we all know. So I think that in this sense it should be random enough. Yeah, it should satisfy all the requirements for the random.
I want to say that first of all, when mathematicians or automated theorem provers prove statements about probability spaces, there's nothing random about that. It's a rigorous proof that you could sort of convert it into some statement about counting or sizes of sets of, you know, good and bad strings, and you know, so when we prove what is the probability of error in some model, that's very rigorous. There does remain the ugly reality of now when you go and get your randomness, is it really, really, really random, and is there really any randomness in the universe to be found? And there it's already you know, a matter of I guess religion or belief. I mean, I think we do believe that there is some entropy out there that okay. There's another, okay, this will be the last question we'll answer, and then the off-topic one. So has there been a theorem considered correct that Lean helped find an error in?
That's a good question. Well, it's so more broadly one can ask, not just Lean, but just theorem provers in general. And if you kind of scour the internet, I mean, so people who work in the field, you know, like to sort of report on mistakes. You know, mathematicians distinguish between kind of small mistakes and big mistakes, right? I mean, the small mistakes, you know, there are often misstatements in I mean, there are tons and tons of slight misstatements in the literature and so on. And so when a formalizer says, oh, you know, I found this thing, oh, the mathematician will say, oh, it's not a big, it's just just fix that. You know, it's just a minor misstatement. So there are lots of small bugs and proofs have been found. I'm trying to think if I know of any kind of dramatic. No, well, I mean, so for example, at a Lean Together meeting, Sebastian Guzel gave a report on, you know, on a result in ergodic theory that he tried to verify, and at the end, an inequality. It turns out just when he tried to verify it, the inequality went the wrong way, and so there was it was a mistake, and he got together with the author, and they had to do a lot of work to repair the proof. So it does sometimes happen that when you verify a proof, you really find that there is a substantial error.
And I will take this one just because it's really very nice. Related to Levi's question, when you so I apologize for the noise. It's not called Stark at home for nothing. So I am at home, and my young 2-year-old who's sick is at home as well. So related to Levi's question, when you verified the error of execution, did you discover any errors in the prover or understand anything new about Cairo?
So happily, from my side at least, we didn't find anything with the
I was,
constraints.
yeah, let me say I was impressed. I mean, the white paper, again, the white paper was kind of a high level overview. There was a sketch. It didn't include all the detail, but the white paper, it held up. The one thing we got was a little bit of clarification when they're kind of, so look, in the end, we just, the theorem says something about the polynomials and the CPU specification, and that didn't change. In the white paper, sometimes there were kind of misstatements or off by one, things that could be clarified. But no, the theorem held true. So I think that's a testament to the care and effort that the Cairo design team put into designing it.
Okay, so we have the one very last off-topic question, which I'll try to answer, while I'm dealing with other things here. So what's the difference between a validity rollup and a ZK rollup? So very briefly, they are two terms for the same, creature. I personally have an issue with calling it a ZK rollup when often most of these creatures, like StarkNet, actually are not zero-knowledge proofs and don't use zero knowledge and don't use privacy. So a lot of people are sort of troubled by the fact that you are calling something with a name that has a mathematical definition, and the thing you're calling doesn't actually have that mathematical property. It's a little bit like talking about 6 as a prime number. So, maybe, you could say that 6 is a prime number, but that would be very unfortunate because it's composite. So I think that's the issue. But they both refer to the same thing, but it's not part of, this is from a different Twitter joke. So I'll let the three co-authors say some final words while I'll deal here with other stuff.
Oh, final words. The project's been great. It's it's really exciting when you see it all come together. I mean, at the beginning you've got, oh my God, how am I going to verify this big thing? And then somehow all the pieces come together and it works. I think it's an exciting time to be in the business of formal verification. That really we're getting to the point where tools can really do the job. And so I encourage all of you to take a look and join in.
For me, it's great that you can take such proof and automate automate checking this proof, and then you just know that you didn't forget any constraint and everything is correct, and you don't have to trust unit tests for this, and you don't have to trust randomness for this. So this is great.
Yeah, so I can only add that working with Lean is not always easy, but it's great fun. So I can really recommend it. And it's really fun to start writing something, and at the end it tells you, yes, you got it right. And then you know that it's right. It's not like programming where you write and then you say, well, maybe it is, maybe it isn't. You know it is. So I recommend.
Okay, so on this happy note, thank you all, and hope to see you on our next Stark at Home episode on a topic yet to be defined. Thank you very much. Thank you, Jeremy, Yoav, Leo. Bye.
Bye. Bye.